In October 2023, a team of astronomers published a finding that quietly terrified anyone who understood what it meant. They had studied more than 100 pairs of twin stars, systems where two suns formed from the exact same cloud of gas at the exact same moment, and they expected the stars in each pair to be chemically identical, like siblings born from the same womb. But they weren't. In roughly 1 out of every 12 pairs, one star was polluted with heavy metals, iron, silicon, titanium, the kind of rocky material you only find on the surface of a planet, not floating loose in the vacuum of space. There was only one explanation. That star had eaten a planet, maybe several. And the unsettling part is this. Stars like the one that consumed a world just like ours are not rare monsters hiding in some distant corner of the galaxy. They look exactly like our own sun. Same size, same temperature, same age. So the question stops being abstract and starts being personal. Could ours do the same thing to us? Before you panic, let's slow down, because the truth about our sun is stranger, more colorful, and more dangerous than almost anyone realizes. And by the end of this, you will never look up at it the same way again. This isn't the first time the sun has sent humanity into a state of raw panic. On May 28th, 585 BCE, a total solar eclipse swept across ancient Lydia in the middle of a pitched battle, and according to the historian Herodotus, both armies were so terrified by the sudden darkness at midday that they immediately laid down their weapons and negotiated peace on the spot. For thousands of years, cultures across the planet interpreted the sun vanishing without warning as a sign the world itself was ending, a dragon devouring the sky, an angry god turning its back on humanity. Even in the modern era, the sun has kept delivering shocks. In 1919, astronomers used a total solar eclipse to confirm Einstein's theory of general relativity by watching starlight bend around the darkened sun's gravity, rewriting our understanding of the universe in a matter of minutes. And in 1859, a massive solar storm known as the Carrington event slammed into Earth with such force that telegraph systems across Europe and North America burst into sparks, and the night sky glowed with auroras so bright that people in the Caribbean reported being able to read a newspaper by their light. If a solar storm of that scale hit our modern, satellite-dependent world today, experts warn it could cause trillions of dollars in damage and knock out power grids for months. The sun, in other words, has never been the calm, predictable disk we take for granted. It has been quietly shaping and terrifying human history for thousands of years, and what's coming next might be its strangest secret yet. Here's something that sounds like a joke, but is completely real. Our sun is not yellow. It is not orange. Technically, it is not even white. Our sun contains every single wavelength of visible light at once. Red, blue, green, yellow, violet. All of it, blasting out simultaneously in equal measure. Think about where rainbows come from. Sunlight hits a raindrop, and the water bends and splits that single beam into all the individual colors hiding inside it. That is proof the light was never just one color to begin with. It was always everything at once. Our eyes are simply incapable of processing every wavelength individually. So when they all arrive together, our brain interprets the mixture as white. That is the sun's true color. If you don't believe it, don't take my word for it. Take the word of the astronauts on the International Space Station, because outside the filtering fog of our atmosphere, that is exactly what they see. A blinding, pure white disk. So why does the sun look yellow or orange or blood red at sunset from where you're standing right now? The answer is that our atmosphere is playing a trick on your eyes every single day, and you never even noticed. Earth's atmosphere is stuffed full of tiny gas molecules, and those molecules are far better at scattering short blue wavelengths than long red ones. When sunlight is directly overhead, that scattered blue light gets thrown across the entire sky, which is exactly why the sky itself looks blue. But some of that blue gets stripped out of the direct beam heading toward your eyes, leaving behind a light that skews slightly yellow. Now stretch that sunlight path out, like at sunrise or sunset, when the light has to cut through a much thicker slice of atmosphere at a low angle. Almost all the blue gets scattered away before it ever reaches you, and only the long, stubborn red and orange wavelengths survive the journey. That is why the sky can suddenly ignite into pink, orange, and blood red at the edges of the day. It is not the sun changing. It is the atmosphere filtering what little of it survives. Now here is where it gets genuinely unsettling, because what I just described is not just a pretty sunset effect. It is a preview of a real future. Let's say, hypothetically, the sun actually turned red. We already know two things. First, the sun contains the full spectrum of light. Second, our atmosphere is naturally hostile to blue light and friendly to red light. So if the sun's output shifted toward red, our entire planet would look like it was permanently trapped in sunset, all day, every day. Scarlet skies, burnt orange oceans, a blood-colored moon hanging overhead every night. It would be dimmer than we're used to, but survivable, even strangely beautiful. Here's the unsettling part. This is not some wild fantasy. This is a preview of our sun's actual death. In roughly 5 billion years, the hydrogen fuel at the sun's core will run out. Gravity will lose its long battle against fusion pressure, and the sun will begin to swell, ballooning outward into what's called a red giant. It will expand so violently that it will swallow Mercury whole. Then Venus. And current models suggest Earth's orbit itself may not survive, being that close to a star hundreds of times its current size. If you thought a permanently red sky sounded ominous, that is nothing compared to the star that causes it, eventually reaching out and consuming the very planet standing beneath it. But red isn't the only twist hiding in our sun's spectrum. Here's a claim that sounds absurd until you understand the science. The sun is, in a very real sense, green. Its surface temperature sits around 10,000 degrees Fahrenheit. And when you calculate the peak wavelength of light a star at that exact temperature emits, the math lands almost precisely on the blue-green portion of the spectrum. The only reason we don't see it that way is because the sun is emitting so many other wavelengths simultaneously that they wash the green out into white. If you could somehow filter out every other color and let only that peak wavelength through, our atmosphere would flood with a genuine pure green light, and the entire world would take on an eerie emerald tint, dimmer, stranger, and honestly kind of unsettling to imagine. Plants, ironically, would struggle in a world lit entirely by green light, since chlorophyll already reflects green wavelengths rather than absorbing them, which is the exact reason leaves look green to us in the first place. A green sun could end up starving the very forests that depend on it. A strange twist where the color of light itself becomes an enemy of life rather than its source. Then there's blue, and this is where the science stops being playful and starts being genuinely terrifying. Blue stars are real. They're called blue giants. And think whatever force governs the universe that our sun is not one of them. Here's the twist that breaks most people's intuition. In the world of stars, color has nothing to do with temperature the way you'd expect from everyday life. Red doesn't mean hot. Blue doesn't mean cold. It's the exact opposite. The hottest, most violent stars in the galaxy burn blue and white, while the coolest, most sedate stars glow orange and red. Our sun, sitting at a modest surface temperature of around 10,000 degrees Fahrenheit, is actually one of the cooler, calmer members of the stellar family. Now imagine multiplying that heat by a factor of tens of thousands. That is a blue giant. Massive, unstable, burning through its fuel so fast that it lives only a few million years before annihilating itself in a supernova. If our sun somehow became a blue giant, the good news is that atmospheric scattering would barely change what we see on the surface, since blue light already gets bounced around by our air. The sky might deepen slightly, but we would never survive long enough to appreciate the view, because a star with that kind of power would have already cooked the surface of our planet into a barren husk long before the color shift even mattered. Real blue giants like Rigel in the constellation Orion burn tens of thousands of times brighter than our sun and live fast, violent lives before detonating as supernovae, sometimes in under 10 million years, a cosmic blink compared to the 10 billion year lifespan our own calm, yellow-white star gets to enjoy. In a strange way, being an unremarkable average star is the single luckiest thing that ever happened to us. Now for the darkest possibility of them all, and I mean that literally. What if the sun turned black? Before you assume this is pure science fiction, understand that this is, in fact, our sun's ultimate guaranteed fate. The only debate is the timeline. After the sun finishes its red, giant phase and sheds its outer layers into space, what remains is a small, incredibly dense core called a white dwarf. It stops producing fuel and instead just radiates away its leftover heat, like a dying ember, cooling for unimaginable stretches of time. Eventually, once every last flicker of light and heat has bled out into the void, that ember becomes what astronomers call a black dwarf, a stellar corpse, invisible, cold, and utterly dark. Here's the twist nobody expects. It would take approximately 1 quadrillion years for a white dwarf to fully cool into a black dwarf. Our entire universe is only about 13.8 billion years old. That means not a single black dwarf has ever existed anywhere, not once in the whole history of everything. It remains purely theoretical, a corpse that hasn't had time to finish dying yet. To put that quadrillion-year figure into perspective, if you compress the entire current age of the universe down to a single second, a black dwarf still wouldn't form for another 2.5 days on that same compressed timescale. Every single star that has ever burned out in the history of everything is technically still cooling, still radiating some faint trace of leftover heat, no matter how ancient or dim it has become. Total, permanent stellar darkness has literally never once occurred anywhere in the observable universe, which means the black dwarf isn't really a prediction, so much as a mathematical inevitability waiting patiently on a clock longer than existence itself has been running. So let's play out what would actually happen if, somehow, impossibly, our sun switched off overnight and became that black dwarf right now. The instant it happens, the entire solar system is plunged into absolute darkness. The moon, which only shines because it reflects sunlight, would simply vanish from the night sky, gone completely black itself. Here's the panic point. Sunlight takes about 8 minutes to travel from the sun to Earth, which means if this happened at this exact moment, we would have roughly 8 minutes of daylight left before the world went permanently dark. 8 minutes to process the end of everything you've ever known about how the sky looks. Temperatures would start collapsing almost immediately. Surface temperatures would crash toward freezing within hours, not years. Because Earth's inner core still holds residual heat, somewhere above 9,000 degrees Fahrenheit, we wouldn't die in an instant flash freeze. But the decline would be relentless and merciless. Roughly every 2 months, surface temperatures would plunge dramatically, and within a single year, we would be staring down conditions colder than negative 450 degrees Fahrenheit, cold enough to liquefy oxygen. Plants would be among the first casualties, not primarily from the cold itself, but from the total collapse of photosynthesis, the engine that fuels almost all life on this planet. Trees, strangely, would cling to survival the longest thanks to their slow metabolisms and their ability to draw nutrients directly from the soil rather than relying purely on sunlight. The oceans would begin freezing at the surface almost immediately, but that ice sheet would actually work in our favor, insulating the deep water beneath it and buying marine life a considerable amount of time before the abyss itself turned lethal. Deep sea creatures, already adapted to a lightless, brutal high-pressure existence, would likely outlast almost everything on land. For us, the human cost would be brutal and immediate. Vitamin D deficiency would sweep across the entire population within weeks, triggering a cascade of health crises. Our bodies rely on light exposure to regulate melatonin, the hormone that governs our sleep cycles, and without it, global insomnia and psychological breakdown would follow fast. Humanity would essentially be left with two options. Option 1, construct massive submarine-like shelters and descend toward the residual warmth radiating from Earth's core. Option 2, cluster around geothermal hotspots in volcanic regions, places like Iceland, where the planet's internal heat could sustain small pockets of survivors indefinitely. Which would you choose, the crushing depths of the ocean, or huddled beside an active volcano in permanent night? Either way, agriculture as we know it would need to be completely reinvented. Underground farms lit entirely by ultraviolet grow lamps could theoretically keep small populations fed, but scaling that kind of artificial agriculture up to feed 8 billion people would demand an amount of electricity far beyond anything our current global power infrastructure could ever hope to generate, meaning brutal rationing and almost certainly brutal conflict over whatever farmland and energy sources remained functional. Animals in the wild would suffer an even more chaotic collapse. Prey species that rely on daylight to navigate and stay alert, like zebras, wildebeests, and giraffes across the African savanna, would become disoriented and vulnerable, easy targets for predators who could finally hunt without the usual rhythm of day and night to worry about. Birds that flock and hunt during daylight hours would vanish from the sky entirely, and with them, one of nature's most effective pest control systems would disappear too, leaving insects to flourish unchecked in the chaos. Migratory species that rely on the position of the sun to navigate thousands of miles across continents and oceans would lose their internal compass entirely, becoming hopelessly lost, and entire breeding cycles tied to seasonal daylight patterns would collapse within a single year, pushing countless species toward extinction almost overnight, rather than over the usual span of centuries. Crops would fail globally within a single growing season. Bread, one of humanity's oldest staples, depends entirely on wheat, and wheat depends entirely on sunlight. Even more critically, oceanic algae, responsible for producing far more of Earth's oxygen than every forest on the planet combined, would die off en masse, triggering a slow but inevitable decline in atmospheric oxygen levels. Even our infrastructure would start failing us. Concrete structures require oxygen exposure to maintain their internal chemical integrity over time, meaning that as oxygen levels dropped, buildings themselves would gradually begin to weaken and crumble, turning our own cities into ticking structural time bombs. If humanity somehow endured this collapse for generations, evolution itself would eventually reshape us. Future humans, adapted to a permanently subterranean existence, might develop dramatically enlarged eyes to capture whatever faint light remained, paler and thinner skin from a total absence of solar exposure, and drastically heightened hearing to navigate the echoing tunnels of underground civilization. Meanwhile, on the frozen surface above, something else would be changing too. Tardigrades, those nearly indestructible microscopic creatures capable of surviving the vacuum of space itself, radiation, and extreme temperature swings that would annihilate almost any other organism, might become the dominant surface-dwelling life form. Given enough time, potentially hundreds of thousands of years, some researchers speculate they could theoretically grow to dramatically larger sizes in an ecosystem with no competition left to keep them in check. Picture a creature that currently looks like a chubby, eight-legged bear under a microscope, but scaled up to the size of an actual polar bear, roaming a frozen, lightless Earth. It's a genuinely disturbing thought experiment, and one that shows just how thoroughly the disappearance of our sun would rewrite the entire story of life on this planet. Now let's step back from these hypotheticals and confront the real documented threat, because remember that opening statistic. Roughly 1 in 12 sun-like stars in these binary studies showed clear chemical evidence of having consumed a planet. This isn't science fiction, it's published astronomical research. Here's how scientists actually catch a star in the act, or at least catch the evidence left behind. Binary star systems, 2 suns orbiting each other, are perfect natural laboratories, because both stars form from the exact same cloud of gas and dust at the exact same time. In theory, their chemical fingerprints should be identical twins. Astronomers analyze the light coming from each star, breaking it down to detect the specific elements present in its outer atmosphere. Every star contains the light stuff, hydrogen, helium, some oxygen, and carbon. But some stars also carry unmistakable traces of heavier, rockier elements, iron, silicon, titanium, materials that belong on the crust of a planet, not floating loose in a star's outer layers. When one twin star in a pair shows significantly more of these rocky elements than its sibling, especially concentrated in its thinnest outer layer, that's essentially a smoking gun. That star didn't form with extra rocky material. It ate it, most likely by devouring a planet or several that wandered too close. This raises an uncomfortable question about our own solar system's history. Our sun doesn't appear to have a companion star, which actually makes it somewhat unusual, since researchers estimate that up to 85% of all stars in the galaxy exist in binary or multi-star systems. But there's a genuinely fascinating theory that our sun might have once had a twin after all, a star that has since drifted away over the past 4.6 billion years since our solar system's birth inside a stellar nursery. One candidate, a star cataloged as HD 186302, sits roughly 184 light-years away and shares enough chemical and orbital similarities that some astronomers suspect it may be that long-lost sibling, separated from our sun over billions of years of gravitational drift through the galaxy. The original research pointing towards stars devouring their planets came largely out of data gathered by the Kepler Space Telescope, and later refined by teams led by astronomer Fan Liu, and in the 2023 study that opened this whole story, astronomer Andrew Vanderberg, whose team specifically targeted co-natal binary pairs precisely because any chemical mismatch between 2 stars born together couldn't be explained away by anything except one of them swallowing something it shouldn't have. If our sun truly did have a twin once, we may never fully reconstruct what happened between them, but traces of that ancient chaos might still be hiding at the extreme edges of our solar system, out in the Oort cloud, that vast distant shell of icy debris, comets, and rocky fragments that could be leftover scraps from a much more violent and unstable youth than our current remarkably calm planetary arrangement would suggest. So, could our own sun ever actually consume one of its planets the way those other stars clearly did? The mechanism itself is well understood. As a star ages and begins its transition into a red giant, it dramatically increases in physical size, and its gravitational influence over nearby objects becomes far more aggressive and unstable. Planets, asteroids, and smaller debris that once maintained safe, stable orbits can get gravitationally disturbed, pulled inward, and ultimately swallowed whole. Scientists have observed that when a star consumes a planet, the sudden addition of that mass and angular momentum can actually destabilize the star itself, sometimes causing it to spin dramatically faster, occasionally even ripping portions of itself apart from the sheer rotational stress. Astronomers have even directly witnessed the immediate aftermath of one of these events, catching a star flaring dramatically brighter for a brief window before settling back down, a signature that matched almost perfectly with computer models, simulating a planet spiraling to its death inside a star's outer layers. For context on just how dramatic these gravitational relationships already are in our own backyard, consider Jupiter. If Earth were shrunk down to the size of a single grape, Jupiter, at the same relative scale, would be roughly the size of a basketball. That's the kind of gravitational muscle already flexing in our solar system, and it's precisely why our current planetary arrangement, stable, evenly spaced, non-colliding, is actually the exception rather than the rule across the galaxy. Research suggests up to a quarter of planetary systems built around sun-like stars experienced significant chaotic upheaval in their early history, planets colliding, getting flung into deep space, or being consumed entirely by their host star. Fortunately, our own solar system appears to be one of the calmer, more fortunate arrangements, one where the planets settled into stable, non-interfering orbits early on and have largely stayed that way for billions of years. Astronomers describe this kind of quiet, orderly setup as remarkably rare when you look across the wider galaxy, where systems full of tightly packed, unstable planets seem to be far more common than neatly spaced systems like ours. In a strange sense, The very thing that lets you sit here comfortably reading this right now is billions of years of gravitational good luck, a solar system that happened to sort itself into a peaceful arrangement instead of a chaotic, planet-devouring one. The realistic timeline for any of this sun-related devastation, red giant expansion, planetary consumption, the eventual slide toward a white dwarf, spans billions of years into the future. And humanity, whatever form it takes by then, will have billions of years of advance warning long before any of it becomes an immediate crisis. But here's the detail that should stay with you after this ends. This isn't some abstract, far future fantasy confined to computer simulations and theoretical physics papers. Somewhere out there right now, in a binary system that looks almost identical to our own, a star that could be the sun's near-perfect twin has already consumed a planet and left the evidence permanently burned into its atmosphere for astronomers to discover. The sun above you right now is not simply the warm yellow disk you grew up believing it to be. It's a white-hot sphere containing every color imaginable, a star capable of one day swelling into a red giant that devours entire worlds, capable of eventually fading into a cold, dark corpse over a timescale longer than the universe itself has existed, and quite possibly capable of the same planetary violence that left its chemical fingerprints on other, eerily similar stars scattered across our galaxy. So the next time you glance up and casually think, there's the yellow sun, remember what's actually happening 93 million miles away. A churning, blinding white furnace holding every color in existence, quietly running out the clock on a 5 billion year countdown that ends, eventually, with the very real possibility of it swallowing us whole. Which fate would you find harder to accept? A world plunged into permanent darkness and cold? Or a sun so massive and hungry it eventually reaches out and consumes the very planet you're standing on right now? Either way, the takeaway is the same. The object you've trusted your entire life to simply rise every morning without question is not some fixed, unchanging fact of nature. It is a living, evolving furnace on a slow countdown. And somewhere out there, its near-identical twin has already shown us exactly how that countdown can end.